Okay, this is section 17.5, temperature variation of resistance. It's really just a short section. Let's share the PowerPoint, and we can see that they just have an old-fashioned light bulb. And the resistivity R is um, it depends on a number of factors, and one of the factors is the heat, the temperature. So there is a relationship between temperature and resistance, and for most conductors, the resistance increases as the temperature goes up, just because as the molecules, the little atoms in the conductor, as they heat up, their kinetic energy, the atoms and molecules is increased. They're bouncing around more, and so it bounces around the free electrons, and they resist moving. The drift velocity becomes lower, so there's more resistance. And this is the relationship. Um, the resistivity is equal to the resist resistivity at a temperature that equals the uh, room temperature resistivity times one plus alpha times the temperature difference. Now this is a delta T, so whether it's in Kelvin or Celsius doesn't matter, but it has to be in one of those, Celsius or Kelvin, because it's just a delta T. Most of the time it's Celsius, and you use it at 20 degrees. Um, Now, since R is equal to resistivity, rho, resistivity times length over A, you can multiply both sides by length over A, and you'll get the resistance is equal to R0 times 1 plus alpha delta T, T minus T0. And these are some, they still have the blue box around the resistivity, but this is the temperature coefficient of resistivity. And you can see that um, towards the bottom of that column under carbon, germanium, and silicon, there's actually a negative coefficient. The resistance goes down, the resistivity goes down with temperature because it frees up more electrons, and they're a little freer to move. But you can see typically there's the resistivity goes up for a temperature increase. And I think that's all I want to say about that. I do a homework example. I think I assign a homework for that one.